Well, the first question on problem set 3 asked us to choose which one of these statements says that there is no largest prime, and if you look through them you should come up with this one. That simply says for all x, and the variables denote natural numbers, for all x there is a y which is prime and bigger than x. So given any x, you can find a number y which is bigger than that x and is prime. And if you work your way through each of the other ones, you'll find out that that's not what it says. It says something else. But that was the one that you needed to come up with to get this one correct. For every natural number, there's a bigger natural number, which is prime. Okay, let's look at number 2. Okay, well, you do actually occasionally see this symbol exist with the exclamation mark to means there is a unique x. So it wasn't just me making this up for the sake of the problem. This is a moderately common symbol that you'll find. It's often useful to be able to say there is a unique x. And if you look through the possibilities, the one that captures that is this one, because let's just see what it says. It says there is an x which satisfies phi, and any other number that satisfies phi has to be equal to x. So there's two parts. That says, the first part says the x does satisfy phi, and the second part is the part that says it's unique, because it says that anything else that satisfies phi has to be in fact equal to x. In other words, x is the only one, because no matter which other y you look at, if it satisfies y, it turns out that you're actually looking at x in the first place. And each one of these has something slightly different with that, and if you try to tease it apart, you'll find that it doesn't quite get what you want it to say. Okay, let's look at number 3. Well, the symbol in this operation is one that you'll occasionally see used in computer science, and you'll even occasionally see it used in mathematics, but I'm not taking it to mean anything in particular. I'm just saying there's some operation, we don't know what it is, it could be addition, multiplication, who knows. There's just some operation, we're simply trying to capture the fact that it's not commutative. Well, to show that it is commutative, you would have for all x, for all y, x arrow y equals y arrow x. That would say that it is commutative. And so to say that it's not commutative is to say that there are a pair of numbers x and y for which that's not the case. All we need to show that it's not commutative is to find a single pair of numbers x and y for which we don't have equality. So which one of them does it? It's C. That says there is an x and there is a y for which we get inequality. One single pair of numbers will give you non-commutativity, because commutativity requires that you have equality for all of them. And each one of these says something different. So there's the correct answer. There are a pair of numbers. And you could get it just by going through this and negating it. There is an x, there is a y, x arrow y not equal to y arrow x. Okay, let's look at number 4. Okay, now this expression is a colloquial expression, and so when I set this question up, I realized that for non-native speaking English students, this would be somewhat challenging. So what I did was I only gave you options that you should be able to distinguish between by knowing the logical structure. The reason I like to give these kind of examples is because they capture an awful lot of social and cultural knowledge, and there's an interesting challenge in capturing that kind of thing in formalisms. But to help you along, I gave you 3 options that you should be able to sort out just on the basis of logic, if you know what being a lover means in this case. So being a lover means you're in a mutual relationship, which means you've got you love someone and that person loves you. But if you look at this one, this says for this person X, so these are all about a person X, they all talk about some person X. This doesn't say that person's a lover. This part says that person is in a relationship with everybody else. So this part, because there's a universal quantifier, that says X loves Z and Z loves X. So this person X is in a loving relationship with everybody. Well, that's nonsensical, so we can forget that one. So it comes down to these two, because in each of these it says the person is in a loving relationship. X is in a relationship with some Z and it's mutual. X loves Z and Z loves X. The same clause here. So the choice is between A and C. Well, let's look at what A says. That says, for all X and for all Y, if the X is in a loving relationship, then Y loves X. Now the Y doesn't come in here, so that the for all Y is to do with this part. So it says, take any person X, if that person is a lover, then every person loves them, if they know them. So that actually is the correct one. Okay, all people love a lover. Of these three, that's the one. You know, you could argue about whether that's the absolute best interpretation, but out of these three, it's certainly a correct one, and so it's the one here. Let's look at this one. This one is a little bit different because it's got for all Y in here. So it says for all X, if X is a lover, then, well, it doesn't say then, it says and for all Y, Ly, X. So the for all actually applies to this part as well. So what this really, what follows from this is that for all X and for all Y, Ly, X. In other words, everybody loves everybody. Well, that's not the case. Because this isn't conditional on being a lover. This just really says that's the case and that's the case. So part of this is saying that for all X and for all Y, Ly, Well, that's not the case. I mean, it's not the case that everybody loves everybody. The world would be a nice place, I guess, if that was true, but it's not true. So it can't be that one. So we've eliminated this one because it doesn't use the fact that being a lover, and we've eliminated this one because it basically just boils down to saying everybody loves everybody, and that leaves this one. And this is definitely one good interpretation of everybody loves a lover. Okay, so we were able to reason that one out, and I would hope that even without the detailed understanding of what this means in English, there's only one of these that will stand up to analysis. And after all, the idea is to sort of look at how the formalisms capture relationships from the real world. Okay, well, there's just one more question to do from problem set 3. Well, for question 5, we have to find which statements are false. Okay, so let's just see what they say. For all X, for all Y, for all Z, if X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. That's true. It's actually known as the transitivity of the order relationship. Okay, if X is to the left of Y and Y is to the left of Z, then X is to the left of Z. Okay, so that one's true. What does this one say? For all X, for all Y, if X is less than or equal to Y and Y is less than or equal to X, then X is equal to Y. Well, that's true. Okay, the only way you can have X less than or equal to Y and Y less than or equal to X is if they're actually equal. What about part C? For all X there is a Y. Well, that's certainly the case, because given an X you can take Y equals X. And then you'll have X less than or equal to Y and Y less than or equal. So that one's true. Well, it's beginning to look as though they're all true. Let's look at the last part. There is an X such that for all Y, Y is less than X, or X is less than Y. Well, you might be tempted to say, yep, given any X, it's the case that every other Y is either less than X or bigger than X. But wait a minute. Among the Y's governed by a universal quantifier is the X you start with. So if there was an X with that property, how could this happen? Because when you look at all the Y's, among those Y's would be X itself. So you would have X less than X. which is impossible. So that one's false. And it's false because the universal quantifier includes the x itself. Given an x, any x that you find, and when you universally quantify over y's, you include that x. And then that fails, and that fails. So there's the one that's false. There is a false one. And it fails because universal quantifiers go over everything, and that means the y will among the y's that you're looking at is the x that you start with. Okay, well, how did you guys do on problem set 3? There were some tricky questions in there.